lecture. My name is Dr. Fiona Panther, and I study black holes, the smallest black holes in the universe, in fact, using gravitational waves, teeny tiny ripples in space-time. At least that's what I tell people if I want to talk to them when I'm sitting next to them on the plane. Actually, I've come to a realization recently, and I hope you'll be kind to me when I share this. I'm actually more of a statistician. Now, I will confess that, I've been thinking about this for a while. I've been mulling over that identity, and, when I was in university, and the other women in my class were talking about how incredibly handsome Matthew McConaughey was, I was thinking about the smooth curves, chi-square distribution with 2 degrees of freedom. So I did do the big thing, and I did come out to my husband. I think I'm a statistician. He said, I know. I think the Birkenstocks gave it away. So before we get on to the black holes, let's talk first about the big black cat in the room. I'm sure you've all got questions about my name. Everyone always does. So to answer your questions that you definitely have, yes, that really is my surname. It was given to me by my father, along with my incredible sense of humor and stunning dress sense. No, I did not choose this surname. No one would choose that surname. And yes, I did get bullied about my name in school, but not the way you might be thinking. Shrek came out in 2001. I was 10. I was in middle school. I never stood a chance. So let's go from green ogres and let's just go back to black holes. It's a far less traumatic thing for me to talk about. So when you think of black holes these days, people often think of the movie Interstellar. And so you might be imagining that, I sit maybe in my office, but I talk to my colleague, Matthew McConaughey, as he's gone off on an incredible journey into a black hole to find out what it's really like and uncover what the 5th dimension is. Spoiler alert, it's love. Now, that's not quite what's going on. In fact, I've got about 2,000 other colleagues who work alongside me to discover black holes. And if you look through that author list on that scientific paper, I'm afraid you won't find Matthew McConaughey's name. So we're a large collaboration, we all work together. We like to think of ourselves as the black hole mafia, but we have a much more boring name, which is LIGO. And we all work together to find gravitational waves to try and find black holes. There's a fun story actually about this image, which is taken from Interstellar. So this is a real rendering that uses all of the equations that describe what black holes look like. It took thousands of hours of supercomputer time. It took incredibly smart people to create this beautiful, beautiful graphic for the film. Now, I didn't have quite that much time, so here's my method. So let's talk about what a black hole is. A black hole is an object that's characterized by 2 numbers. Those numbers are its mass and its spin. Okay, they're the only 2 numbers we need to define what a black hole is, and we try to measure those in various different ways. Now, one way that you can measure black holes' mass is by looking at the light that comes from the region around them, because it turns out it's very rude to ask a black hole how much they weigh. This region around the black hole is called the accretion disk. It's made up of things like dust, gas, charged particles, cat hair, and those socks that went missing in the tumble dryer that you don't know where they've gone. And as this accretion disk swirls around the black hole, it glows and emits light that we can use to do our science with. At the very inner edge of the accretion disk, where the black bit of the black hole starts, that's something called the event horizon, not just a bad film with Sam Neill in it. And if material falls across the event horizon, it can never return. Everything at that point falls into the center of the black hole. Now, this means that a lot of people think that black holes suck. But that's not quite true, because black holes are actually really, really inefficient at sucking things in. You know that Dyson vacuum cleaner that you spent about $2,000 on? that's hanging up in your laundry and you get it out once a week to push the cat hair around the house and shove the Lego bricks around and nothing ever actually falls into it, yeah, well, that's kind of what a black hole's like. They don't really accrete that much material, and that's kind of handy for me because it means once a black hole forms, they don't change their mass all that much. So what's better than one black hole? Two black holes. So when you've got two black holes together, they can produce gravitational waves. So this happens because when a mummy black hole and a daddy black hole love each other very, very much, they have a nice black hole cuddle, and they produce gravitational waves. And this is what I work to measure. And these are really handy because it turns out that what you can measure from gravitational waves is the mass of a black hole, which is great because it turns out it's really, really rude to ask black holes how much they weigh. And we can use these gravitational waves to measure the masses of the two black holes that merge together, plus the black hole that formed when they merged after that lovely cuddle. So, what's better than two black holes? Loads of black holes. Meet the black hole family. This is, to date, every single black hole and a few neutron stars we don't really talk about that we've discovered using gravitational waves. So what's the first thing that you notice when you look at this population of black holes? Personally, I think it looks like Batman logo. So if you look a little bit closer though, look down here at Batman's bottom, what you see is you see some black holes that are in what we call the mass gap. Now, people far smarter than me who understand how stars work and care how stars work, figured out that when a star dies, it can't produce a black hole between about 2 and 5 times the mass of the sun. That's really, really big if you think about stars, but it's not very big at all if you think about, black holes. So, what do we know about these? Well, we do know that we don't see any of these with light, right? We don't see any of these by just looking at their accretion disks. So what's going on here? We need to try and understand the population, and this is where statistics comes in. So I'm going to bring it back a bit closer to home and use an example that we all understand to start understanding the black hole population. What I'm going to do is I'm going to plot a distribution. I'm going to plot up the y-axis the number of people, and on the x-axis I'm going to plot a quantity that we should all be pretty familiar with, something that we all have. Now it turns out it's really, really rude to ask people how much they weigh. And so instead what you could do is you could measure the height of every single person on the planet. And if you do that, then you end up with this lovely distribution that shows you the height of humans. And there's a few things we can do with this. We can look at the average. What height are most people in the world? So if we were to just find one person and pluck them out of the population, they'd probably be average height. This is why my husband is pretty average. Because I just took the first one that agreed to marry me. We can also look at the width of the distribution. That tells us about how much variation we expect. Now, we can start looking at subpopulations, subsets of the entire population of the planet. One such subset is, we're down, is everyone in the room. And so if you looked at everyone in the room, then you would find something that looks probably a little bit like this. So there's fewer people overall, but probably, the same average, pretty much the same spread. You could try sampling the population a little bit differently. So, maybe you want to go online and you want to see some sort of population that, frequents the online space. For example, you might want to consider the delightful specimens present on dating apps. And when we sample things differently, for example, looking at black holes in light versus looking at black holes in gravitational waves, we sometimes see that distributions look different. And we need to understand why that is. Are all of these incredibly eligible bachelors really 6 foot tall and over? Or is there some sort of selection effect, some sort of bias? Okay, maybe there's a bias. Maybe they're all adding on the height of the fish that they're holding in their profile picture. So this is how we can get some sort of information out of a population. So let's go back to more black holes. So this is what we thought the mass distribution of black holes and their little cousins, neutron stars, looked like before gravitational waves came along. You've got your neutron stars, and then you've got these things called mass gaps. This is where we think that stars can't die to make black holes or neutron stars at these masses. And so we didn't expect to find any objects in these gaps when we started looking with gravitational waves. But as we've looked more and more, we've found more and more problems. We're actually starting to fill in the mass gap. We're finding more and more of these things, and it's meaning we're having to look beyond exploding stars to try and figure out how these are made. And the way we think this might happen with this lower mass gap, one possibility is something called a hierarchical merger. What is a hierarchical merger? It's a very, very fancy way of saying that when you have, say, two adolescent neutron stars that like each other very, very much, they might go behind the bike sheds. And they might, get really, really closely acquainted, and maybe they'll merge and make the smallest possible black hole. Sometimes you have the smallest possible black holes. They find one another out in the vastness of the cosmos, and they merge to make another black hole. And if those larger black holes can find one another, they can merge to make an even bigger black hole. And so we think that these mass gap objects come from previous generations of black hole mergers. These black holes have different masses and spins to the black hole binaries that were born together. And so what that suggests is it might not actually be a selection effect. There's something genuinely different about these black holes, and that's one of the reasons we might not see them using light. And the cool thing is they're filling in that mass gap. We're finding things that we never expected to see. So explaining how these hierarchical mergers is kind of easy because, the theory is easy. Black holes find each other, they make friends, they merge, they form bigger black holes. But actually understanding the reality of how the black holes find each other is very, very hard. It means they need to be able to find one another very, very efficiently because space is very, 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 very big. And it could also require new models for stellar evolution. Now, this is what I work on right now, and I'm currently writing a grant that would pay me for another few years to continue doing this work. And I have a theory that I'm going to test out. I think this is a really good theory, so, no stealing this for your own grant applications. I think they're finding one another through some sort of black hole version of Tinder. Maybe it's called Interstellar. So now we've got enough black hole mergers to understand the whole black hole population. And what can this really tell us about? We want to figure out how big those smallest black holes are because it tells us something really, really important about stellar evolution, about space-time, and heck, we might even find some of those socks that you lost in the tunnel drive. Thank you very much.